We're going to have a look at diffraction here. Diffraction, hopefully you learned, and you hopefully you looked at the video where we talked about the whole point of view with wavelength relating to gap size. So normally you've got a gap of some sort, sometimes two gaps, sometimes heaps of gaps, and you have waves coming through, whether they be light waves or water waves, and if the gap size is comparable to the wavelength size, we're going to get diffraction. And we have to treat the gaps as if they are a source for the wave, which is what happens at any point in time, anywhere along a wave. Each particle literally is acting as a source, a new source for the wave, and generating that wave. So with diffraction, what we're seeing is interference. And what we want to see, so with two sources here, over here, we're going to get the two waves will have traveled the same distance. If they're in phase here, traveled the same distance, they're still in phase, so you're going to get a maximum. All right, a central maximum. Sometimes these are called fringes, and if it's light in it, that would be a bright fringe. Whereas up here, okay, this one travels further than this one. So they started in phase, but the one that's traveled further is in a different phase. And when they get half a wavelength difference in distance that they've traveled, they're half a wavelength out of phase. And so they're going to destructively interfere, and you're going to get a minimum there. Same over here, because the same situation applies. Right? So this is interference. This would create the young slits pattern where you've got a bright maximum, dark bands, bright, that sort of thing. Now, one of the issues that happens with all this is when you actually get light or white light, right? So you've got your slits and you've got your thing over here. Now with white light, you're still going to get that central bright maximum. But we talked about the fact that the distance for one of them to travel might be half a wavelength difference. But blue has a wavelength of about 400 nanometers, and red has a wavelength of about 600 nanometers, right? So half a wavelength for blue is a smaller distance than half a wavelength for red. So the blue is going to get it's going to be half a wavelength different before the other one. We're not really caring about that, but what about where they're one wavelength difference, where they combine again? Okay, where they combine again. So where they're one wavelength difference, they're in phase again. Now they're in phase again, one wavelength different. So there would have been the half wavelength. You wouldn't have seen it, but one wavelength difference for the blue will happen before it will happen for the red. So you'd have red there and blue there, and obviously green in the middle. So a diffraction grating will split up white light into the three colors, just like a prism will. And you'll get this little patch of first order colors. And then you'll get another little patch here again, where you've got the blue is now two wavelength differences, and the red would be two wavelength differences up there. So that's what a diffraction grating can do. Now, the thing about diffraction is we'll look at a formula for two gaps, and we'll come up with a formula. That's young slits. Look at the little video on it. You've got to understand that formula. That formula is an approximation. Where you've got a grating that, sorry, it's not like that. Where you've got a grating with lots and lots of equally spaced slits, that's called a diffraction grating. And I'll show it to you in class with a laser and things like that. With that, again, you've got the same principle. At a certain angle, if you shine white light there, you're going to get one wavelength difference, and that's going to give you a bright construct. Of course, you're going to get the bright one in the middle, but you would get, say if this was a red laser, one wavelength difference, then you get another light over there, two wavelength differences. It would be happening down here too, and we'll work out a formula for that. If you then shone a blue laser through, if these were red ones with them bigger wavelengths, if I now shone a blue laser through, I'd get a blue about there, a blue about there, then there'd be another blue about here, and these guys would be blue. That's the second order blue just coming after the first order red. So a diffraction grating will split up light, and the distance to these maximums, one wavelength difference, depends on the wavelength, and we'll see that with our formula. So understanding diffraction and understanding the formula, quite important. But these are the principles upon which it's based.